Hello, everyone. Welcome to this week's Crunch seminar. Our first speaker today would be talking about using PINNs for handling accidental scenarios in nuclear power plants. Our speaker is Dr. Federico Antonello, and he's a postdoctoral researcher at the European Space Agency. He specializes in utilizing advanced modeling, simulation tools, and AI models to improve complex system operations and safety. Holding a PhD degree and a master's degree in nuclear and energy science and technology from Politecnico di Milano, he collaborated with CERN during his studies. He has also been a postdoctoral fellow at MIT and has received prestigious awards, including the George Apostolakis Fellowship and the Outstanding Postdoctoral Fellowship Research Award from MIT's Nuclear Science and Engineering Department. With that, please join me in welcoming him for today's presentation. You may want to start.
Okay, thank you for the kind introduction. I'm Federico Antonello, and in this presentation, I will discuss the use of physics-informed for neural networks as surrogate models for accidental scenarios in nuclear power plants. This study and activity have been developed in collaboration with Professor Jacopo Bongiorno from MIT, Professor Enrico Zio from Politecnico di Milano, and under the funding and of Progetto Roberto Rocca. So I would like to give a bit of introduction to the presentation. So at the beginning, I will introduce the context of the work. So the next generation nuclear design concepts and the use of and the role of modeling and simulation for assessing the safety of such nuclear reactor designs. And then moreover, I will go deeply in the concept of surrogate modeling to enhance the modeling and simulation capabilities with the current approaches and the approaches that we propose in our studies, so the use of physics-informed neural network. And then eventually, I will describe the case study, that is the nuclear battery, the new generation nuclear concept design that we considered, the advanced safety assessment that we use to develop our modeling and simulation tools, and finally the physics-informed neural network development and the application. So to start with the context of the work, here you can see in this slide a few examples of next generation nuclear reactors. You can see sodium cooled fast reactor, AP1000, and the nuclear battery. I don't want to go into details or the characteristics of such designs. What I want to underline is their commonalities. So they are low carbon or carbon-free solutions for electrical production. They are safer, more efficient, and more sustainable with respect to the previous designs. And they use advanced materials, design, and cooling systems. They are economical, flexible, and scalable. But moreover, the most important characteristics is the use of novel safety features that are in-entry safe, and the use of passive safety and coolant systems that has to be deeply analyzed and investigate in order to assess their credibility and their use, and in order to analyze some possible specific threats and hazards that are related to such concepts. In order to do so, in general, there is the need of advanced safety assessment. And starting with a new design as the one that we are analyzing, we need to analyze the design and the characteristics, and in particular, analyze the design, similar concepts, information in order to identify the threats, analyze the threats and compare them with the known threats from light water reactors, and specifically analyze the novel threats in order to being able to analyze, investigate the safety function and safety features of the reactor. To do this, there is a need of modeling. So we need to model scenarios, transients, safety parameters, safety thresholds, influencing factors. And we do this with the relevant use of modeling and simulation tools that take advantage also on advanced, for example, Monte Carlo simulation techniques, advanced Bayesian modeling, dynamic event tree, and so on. And also from data and information, in the case in which we have data and information, So from similar designs, from prototypes, from reports, in order to eventually provide an integrated deterministic and probabilistic safety assessment that uses the information related to the modeling and simulation tools and combine them with probabilistic frameworks in order to provide, for example, failure probabilities and safety margins. So I would like to stress again the role of the modeling and simulation for the safety assessment of the nuclear reactors, and in particular for the scenario explorations, the parameter interactions, the assessment of the safety margins, the failure and the success probabilities. So we have that modeling and simulation are strictly related to the quantitative safety assessment and the qualitative safety assessment, and are central in all the safety frameworks. They make use of the insight from the safety tools, but they also provide quantitative insights for the risk assessment. Some examples are the use of modeling and simulation to understand intricate behavior in the reactor during accidents, to predict the response of the reactor during an accident, and to analyze undesirable consequences in order to eventually optimize the design of the nuclear reactor, the safety systems and the barriers that has to mitigate the accident consequences.
Federico, what is the three circles? The two circles are identical. Do you mean qualitative scenario and then you do to
yes, sorry, there is a type with qualitative and quantitative.
Okay, that's what I thought, yeah. Okay.
Yes, I'm sorry.
Good, thanks.
Okay, so for the development of such modeling and simulation tools, we need to start from the design information and the specifics. Consider also the hazards and the threats in order to understand what we want to analyze and what we want to model. We also need the use of event logic modeling in order to understand the sequence of events that we want to model, and also the use of data, the test data from testing when they are available, to being able to develop some complex and multi-physics simulation models that describe the behavior of a nuclear reactor. Here in this slide, you can see an example of a modeling strategy for a nuclear battery. You can see that the connection between various components and systems, and these modeling strategies have been developed considering all the information that we have, and is used then to investigate accidental scenarios and to perform safety assessment. For what concerns the safety assessment, the first step is to provide a deterministic safety assessment. In this case, we use as a simulation model a best estimate model, that is the so-called simulation model in nuclear engineering. And in this kind of approach, we perform the safety assessment assuming the worst case scenario. So we investigate the scenario, and then we quantify and evaluate the quantity of interest that are in general the temperatures inside the reactor. We analyze such temperatures and we compare them to some limits in order to assess the safety characteristics of the design. Here you have an example. To do this, we have to set the simulation model, initialize the accidental scenario conditions, and the model parameters. The model parameters, for example, take into account the degradation of the components, the characteristics, some thermal properties that can change and vary during the lifetime of a reactor. But in this case, in this approach, we consider as the worst that we can possibly have. And we analyze, for example, here you can see the behavior of the temperature, that is in this case the cladding temperature of the fuel pin in a reactor during an accident. We take the maximum value and we compare this value with the safety limit in order to assess and to give some insights on the risk of the reactor during such an accident. We have some issues because we are over conservative and we are not estimating the uncertainty properly. So we moved, there is a move from the best estimate plus uncertainty. And in this case, we aim at reducing the conservatism of the deterministic safety assessment by modeling the uncertainty in the input parameters, and to provide an estimate of the probability distribution of the quantity of interest. So in the example before of the temperature of the cladding, to do so, we set again the condition for the simulation. Then we model the uncertainty in the input parameters, for example, in the degradation or in the thermal properties of the reactor. We sample some sets of input parameters, usually few. We compute some simulations. We take those simulations and we use, for example, order statistics, such as the Wilks theorem, in order to provide some information related to the probability distribution of this quantity of interest. In this case, you have an example in which we use the Wilks theory in order to assess the confidence level that the largest of the values that we simulated thanks to the best estimate model is on a certain percentage of the distribution, and this is usually the 95th percentile of the distribution. And we use this to compute some safety margins, so to understand the margin that we have with respect to the limit. We have some issues also in for this framework. We have usually few simulations. We are quantifying the uncertainty only consider some order statistics, and we cannot quantify the overall probability density function for the distribution of our quantity of interest. So now we can understand the desiderata and the challenges that we have for this kind of approaches. So we would like to have a detailed uncertainty quantification for our output. We would like to perform sensitivity analysis to quantify the parameters contribution to an accident. We would like also to quantify and assess failure, success, safety margins probability, and to, in general, investigate the scenarios, the interaction, and the probabilities. The main challenge in this case is the fact that some modeling and simulation tools are computationally expensive, and so we cannot afford to simulate tens of thousands or hundreds of thousands of simulations, which are required for the full identification of the probability distribution of the quantity of interest and the safety analysis that we are interested in. And so we need some techniques in order to provide such simulations. The solution that we found in the literature was the use of surrogate models and reduced order models for the simulation of such accident scenarios. A surrogate model is an approach in which we aim at developing a computationally cheaper surrogate of the original simulator in order to approximate the input-output relation and response of the simulation. Here we have some examples. A widely used technique is the reduced order model, in which we reduce the complexity of the simulator by reducing the degrees of freedom and the accuracy of the physical models in order to alleviate the computational burden. In this case, we have the problem that this is a code-intrusive methodology, and the potential to speed up the simulation is limited when we have strong nonlinearities. Then we have traditional machine learning-based surrogate models. Here I wrote traditional because they are the widely used. So it's traditional with respect to the nuclear industry. Those are Gaussian processes, support vector machines, polynomial chaos expansions approaches, from which we can use a limited number of simulation and data and trajectories in order to learn the best estimate model and replicate and generalize the input-output relation. In this case, those models are simple and provide decent results. However, they cannot deal with a large amount of data. For example, when we have really long simulations and we would like to predict and mimic the entire transient of the simulation, we have strong limits on using some such approaches. Then there are recently proposed approaches that are based on deep learning. So we have deep neural networks, long short-term memory networks, to give some examples. And they can use a large amount of data. They should use a large amount of data to replicate such input-output relationship for the simulator. Such approaches have good accuracy and can handle a large amount of data. And we can, in this case, reconstruct also long transients, but they require a large amount of data for their training. Here, I would like also to give you an example on how it is possible to develop a surrogate model. Here you have the steps that are needed. So the first step is to sample enough sets of input parameters to describe the input space and to perform the corresponding simulations. Then we can train and develop and train the surrogate model with the available simulation. And eventually we can perform the uncertainty quantification and the safety analysis. For what concerns the first step, we have our input parameters that are usually described with the probability distributions. You can see here that we can have different probability distributions, and we should be able to sample sets of input parameters in a way to be able to describe the overall input space. Then we can use the best estimate model to do our simulations. We can identify, for example, the peak cladding temperature, considering the example of before. So we can analyze and assess the maximum value of the temperature in the fuel pin and in the cladding, and use this for our safety analysis. For what concerns the strategy that is usually used for the sampling, we have the Lightning hypercube sampling strategy. In this strategy, we usually divide the input space in equally probable intervals along each dimension. I gave here a small example in which we have a two-dimensional input space uniformly distributed and from which we would like to have 5 samples. As you can see, we divided the input space for each of the input variable in 5 intervals. Then for each of these interval, we can sample only one value. So as you can see, for the x1, we can sample only one value that is in the second interval of x2. So for this, we cannot sample any other input. And so we can do this, and we can describe fully the input space. And this technique is usually interesting and used when we have few simulations available. So when we can have only a few sets of input parameters. Then the second step is the training of the model. For example, for this example, we use a Gaussian process to simulate an accident, and we had like 250 sets of input parameters. We divide this for the training and the test of the model. We developed the surrogate model or the meta model, and we apply it to the testing set in order to compare the performance. As you can see here, we have decent performance considering.
Did you tell us how many parameters you have? How many uncertain parameters?
In this example, 7.
Okay, so it's a small set.
Yeah, it's small. Is a small set. Is a small set in this
and
example.
Also, did you tell us about the model? I mean, the model is written in terms of PDFs, or is written in terms of state variables like temperature and other? I mean, I didn't see the equations.
Okay. For the simulation model in this case is really complex. Is a simulation model of an entire nuclear reactor, of the core. So it encompasses thousands of equations.
Thousands.
And
yeah.
Yes, of different equations.
What's the equation? Equations are transport, momentum, temperature,
temperature, heat conduction, and temperature, heat conduction, the equations related to their activity. So the kinetic.
Are there 1D lumped 1D equations, or are
in this specific example, yes, and yes.
So it's okay. So lots of equations, but simplified in lumped models of 1D. But then you have 7 parameters. You must have more than 7 parameters.
Yeah, I mean, then of course, to arrive to the 7 parameters, here we did some studies to understand which were the parameters that were influencing the most the results. This is
top 7 after sensitivity analysis. You take the top 7 uncertain parameters, let's say.
Yes, but also with the experience and some analysis related to the safety. So we did also some we use system theory in order to understand and model the nuclear reactor. And considering the system theory, we use a technique in which we are able to understand which are the parameters that drive the behavior of the reactor.
Okay.
But I have another slide later that is more specific on this respect. This is only a small introduction to give an example on the steps that we need to use. A model that have been used for this approach that is only able to give us the maximum value in a transient, but given that the mapping is quite easy, so we go from 7 input parameters to 1 value that is the maximum temperature, the model is still able to do it properly. Then we can use this we can use the surrogate model to provide the overall probability density function of the output, as you can see in the 3rd step. So in this case, given that now our surrogate model is really fast, it doesn't take hours or days to simulate a scenario. We can take 10,000s or hundreds of thousands of input parameters, use the surrogate model and quantify the uncertainty.
Okay, thank you.
Yeah, so the main issue for this kind of approach is the fact that we need to use a model that is not able to give us the entire transient, but is trained only on one value. But in some safety applications, we need to know the values and the behavior of the temperature along time. And sometimes we have fewer simulations than the 250 that I gave the example for. And so also with the fewer training samples is difficult to construct a surrogate model. Then for what concerns machine learning and deep learning models, they are black boxes. So we don't really know if they are respecting the physics and the laws underlying the behavior of the accident. And so they are difficult to interpret, and this can pose limitations in the licensing and in the evaluation of the safety assessment. So our proposal is to use the physics-informed neural network for the surrogate modeling of accident scenarios in nuclear power plant. I will not go in the details of what the physics-informed neural network is. I mean, given the audience, I would like, to give the desiderata that we want to have, given the fact that with the physics-informed neural network, we are able to incorporate physics laws and equations in the network. a main point is of the desiderata is the consistency with such physical laws, then an improve in the accuracy with respect to the original best estimate model, and the ability to reconstruct the entire transient and the entire simulation. Then the capability to be trained with fewer data when few simulations are available, but then also the capability of handle a large amount of data when we have simulations that are really long, that generate big data sets, and then also the capability of run the simulations in a reasonable computational time in order to being able to perform the uncertainty quantification and the sensitivity analysis. So here I have some more details on the case study and the application. Our case study is a nuclear battery that is a standardized mobile and plug and play microreactor. It is factory assembled and factory fueled and then shipped, is envisioned to be shipped in the location in which is needed. It can be used in remote locations, and after some disasters, it can be shipped in the location in order to restore the grid. It's characterized by passive core heat extractions and safety features that are passive again. So we have the same characteristics that we mentioned at the beginning of the presentation. Given the fact that this is a relative new design, we need some dedicated safety assessment and evaluation. We need to verify the safety features through rigorous analysis, and then we need also to understand and analyze the new threats and hazards that are specific to this design. In order to do this, we developed a novel concept and framework for the analysis and the risk assessment of such new reactors. As I was mentioning before, in this kind of analysis and framework, we make use of some qualitative exploration approaches that are based on STAMP STPA. For this kind of approaches, they use system theory instead of reliability theory in order to analyze and investigate the scenarios. And in particular, they make use of the control structure modeling, from which you have an example in the slide. So there is a deep analysis of the design, for example, in this case of the nuclear battery, in which we can define and analyze all the processes, all the components and systems involved in each of the process that we want to analyze, in order to understand the correlation and connections among the parameters, the values, the events, the systems, and this will give us a picture of the importance parameters that then we would like to use in the best estimate model. So here you have an example in which we took the design of the nuclear battery. We consider the core of the nuclear battery, and then we divide the processes considering the heat removal, the reactivity control, and the power production. Then we analyzed all the possible interconnections and the feedback. So how a component or a system can affect another component or a system, and which are the parameters and the variables that are leading such feedback and connections. So we use this to develop our modeling strategy for the development of the best estimate model of the reactor, and being able to modify, change, and analyze the variation of such parameters in the code, and analyze the consequences and the consequences with respect to the, for example, the temperature of the key components in the reactor during accidents. So this was the main part in which we identified the parameters that are important for the analysis. And then we use this kind of model and approach to analyze the accident scenarios and to explore the scenarios. The accident scenarios that we analyzed is the unprotected loss of its sink. So in this case, we have a sudden loss of the heat transferred in the secondary side of the reactor, and also the inability of controlling their activity within the control rods and control drums. So their activity that is directly related to the power generated in the reactor is controlled only through some feedbacks of their activity that are related to the temperature. And then the heat removal, the heat is removed only with an auxiliary cooling system, that is the reactor vessel auxiliary cooling system. And this kind of accident is used to prove and show the capability of this kind of reactor of sustain one of the worst accident that can happen. In this case, the nuclear reactor is supposed to shut down itself without the use of any of control rods and control drums, so of any of the systems related to the control of their activity. Here you have the list of the parameters that we have identified and that we are analyzing. So the initial power at the beginning of the transient, the reactivity feedback coefficient, that is the coefficient that is driving the reactivity feedback, then some thermal properties, for example, the conductivity of the graphite, that is a parameter that is affected by the degradation during the lifetime of the reactor. Then the gap conductances between the various parts of the nuclear battery. Then the RVAX flow area, that is the area of the system related to the heat removal during the accident. Then the temperature of the air that has to cool down the reactor during the accident, and then the roughness of the RVAX that is related to the capability for the heat conduction and for the heat removal. Then the output parameters that we are analyzing are the average fuel temperature, the net reactivity, the peak leading temperature, and the RVAX power. Here we have some peculiarities for the application and for the development of the physics informed neural network. First of all, we are considering here a best estimate model that gives multi-physics simulations and consists of thousands of equations and PDE describing complex physics in complex geometry. Then we have only few simulations available, 250. And the approach should be consistent also for the development of surrogate models with fewer simulations, because for this kind of simulator and the reactor, we are able to have 250 simulations. But for other accidents and reactors, a simulation runs in days, and so we are not able to have such amount of simulations, but we have to deal with 50 or even 10 simulations. And the simulations may result in long time series. So the desiderata that we want to have, the further desiderata that we want to have for our physics informed neural network is to be developed considering only few equations, so with a partial knowledge of the physics, then to be developed and tested with various data availability, and then we would like also to compare it with a deep neural network to understand the advantages and the drawbacks. A key part to develop the physics informed neural network is the processing of the data. And so another peculiarity of this kind of data is that given a set of parameters, that in this case are few parameters, we use such parameters in a simulators, and then we have a long transients. So given like 7, 10, 11 parameters, we can have an output with a really big dimension of thousands, depending on the time scale that we want to use. And this is a peculiarity that we have to develop our surrogate model and to develop our physics informed neural network. Because at every time step, the the surrogate model gives us all the values of the output parameters. So we have an I-dimensional output. To deal with this, what we did was to consider each point in time as a separate point, as a single training point. So given a set of input parameters, as you can see here, we gave the set of input parameters along with a specific time, and then we consider as an output the specific output at that specific time. In this way, we created the input-output relation. So given, for example, a simulation of 100 time steps, our input parameter, our input data set would have been a set of 100 points in which we had the same input parameters and in which we vary the time in order to have 100 values of the output at different times. So this is the processing that we consider for our physics-informed neural network. Then, for what concerns the physics law, we consider the reactivity feedback. In this case, this equation gives us the time-dependent behavior of the reactivity feedback in response to the fuel temperature changes. So if the fuel temperature changes, for example, it increases during the accident, then we have a direct effect on the reactivity that reduces the power and so shuts down the reactor. So the coefficient alpha here gives us the variation of the reactivity given the variation of the average fuel temperature in the core of 1 Kelvin. We selected this equation because this equation, among all the equations that we have, is able to describe the dynamics of the nuclear battery during our accident. And so in order to test the capability of the physics-informed neural network of dealing with few or only one equation, we selected this one for the ability of giving an overall description of the dynamic in the core. Then, of course, we consider also as a loss the mean square error with respect to the simulated data. And for this first approach and attempt to use the physics-informed neural network, we didn't use any allocation points. Here you have the characteristics of the architecture and the training of the neural network. Here we use to develop and compare the physics-informed neural network with the deep neural network. We use the same architecture both for the physics-informed neural network.
There was a typo in the equations because I see DAY, are there special derivatives or not? On the left, if you look on the left on the figure where you have the physics, there are time derivatives. Here? No, to the right, just to the right of that.
Okay.
No, to the inside your box. There, right there.
This is only to give an example of the physics-informed neural network. It is not related to the physics on the right.
Okay, so the only physics you have is this time derivative.
The only physics that we have is the time derivative. This is only an example of a physics-informed neural network.
I'm trying to figure out, because this is an OD, not a, I mean, this is a simple OD, it's not PD. Are you, I mean, the system of equations that you use for the simulate data, is it lumped and it's all ODs? Is it a bunch of ODs, like 2,000 of ODs, or is it spatial dependence?
There is the spatial dependence.
Okay.
Yes,
so
yes.
That's why you have partial derivatives here.
Yes.
Otherwise, okay.
Yes, the set of equations that we have in the simulator is complex and is multi-physics and considers also the geometry of the reactor.
Okay.
But in this specific case, we wanted to use and to understand the effect of having only one simple equation. And if this simple equation is able to regularize the network, avoid overfitting or other underfitting in the results.
Right. Okay. Thank you.
Thank you. Okay, so this is the architecture. I mean, to select the hyperparameters, we use a try and error procedures. I want also to underline that in this case, we didn't want to train the best network possible. We use this try and error procedure to have reasonable results, good results, and being able to compare the physics in for neural network with the deep neural network. Here you have all the specifics of the training and of the architecture. We train the networks with 70-80% of the data validated on 10-20 in order to identify the best hyperparameters, and then we test on the remaining 10-20 simulations. We use the training of 2000 epochs and the callback method to select the best network performing the best on the validation dataset. Here you have the results with respect to the training with 180 simulations. So I want also to underline that we trained the network with 3 different datasets, one of 180 simulations, one of 50, and one of 10. This is the results with respect to 180 simulations. Then, given the complexity and the strong linearities, the accuracy is affected by randomness. And so we trained both the PINN, the physics in for neural network, and the deep neural network, considering the 10 different random seeds. And here you have some statistics related to, to the error. And then the errors with respect to the 4 model outputs are comparable. So probably from now on, I will describe and comment the errors with respect to the temperature of the fuel, but the results are consistent for all the outputs. Here you can see that the worst PINN, the mean square error, is 2 orders of magnitudes lower than the worst deep neural network. So in this case, the worst deep neural network is underfitting. And in general, the physics in for neural network performs better as with the mean, median, and the maximum and minimum values for the mean square error, as you can see from the table. Then with this plot, we also analyzed the behavior of the mean square error in the training and in the validation in order to understand the effect of giving the physics law to the physics in for neural network. And the 2 plots highlight the capability of the physics in for neural network to avoid overfitting, but also to provide a more regularized.
We cannot hear you. We cannot hear you. Hi, Federico, we cannot hear you. Federico, we cannot hear you.
Hi, Federico. We cannot hear you.
We cannot hear you.
The last 2 slides. The nuclear accident.
Training with only 50 samples. Also, in this case, the physics info neural network is outperforming the deep neural network. In general, mean and median values are better, and there is a good regularization of the physics info neural network. Similarly, for the simulation, the training with 10 simulations, as you can see, in this case, both the physics info neural network and the deep neural network are characterized by large errors, of course, because of the really small training set. In general, the mean square error for the physics info neural network is 44% lower than the deep neural network. So we have better performance also for this training set. And in general, the results with the 3 different training sets are consistent among each other. So all of them show the advantages of the physics info neural network. And the fact that the physics constraint in the physics info neural network loss provides a better regularization and generalization capabilities, and also avoid underfitting. And considering, this is another not considering the licensing and the safety assessment of the next generation reactor, is that we have also the advantage of being able to have a more trustfulness network with respect also to the physics. Now I would like only to summarize the work and the presentation. So we have the objective of developing a surrogate model to enhance the modeling and simulation capabilities within the advanced safety assessment framework for the next generation nuclear reactors. And our solution was to use a physics info neural network as a surrogate model. So to substitute a best estimate simulation model with a physics informed surrogate in order to being able to assess and to quantify the uncertainty, and then to being able to perform safety analysis. And our result is that the physics info neural networks outperform the other machine learning and deep learning approaches, and allow also surrogating the entire transient. Here there is the list of all the advantages that we discussed. So there is a better accuracy, there is a reduction in the error, we avoid overfitting and underfitting. We provide a more regularized and consistent simulations, and there is a proven benefit in including the governing fundamental laws in the network. The disadvantage that we have is the large computational effort for the training of the network. Then there is the influence on the numerosity of the training points. So we have significant advantages adding the physics in the network, also when we have a small amount of data available. And for what concerns future work, we would like to assess the influence of different physics and different equations in the network. Analyze also the influence of using allocation points, and eventually to understand and analyze the model discrepancy of the PIN, so the difference with respect to the best estimate model, and assess also the uncertainty with respect to the error that we have and the model discrepancy that we have with the physics-informed neural network. And thank you for your attention. If you have other questions, you can write me to my email that you can see here. And here you have the references of the main references of the. Thank you.
Thank you, Federico. Do we have questions for him?
Hi, this is Anirudh from Brown. I'm a postdoc here. So I had one question. So I saw that you are solving it for like, I think the time is up to like 2000 seconds or more, right?
Yes.
So are you solving it in one go, or have you tried like seeing if you approach it in a sequentially, is there any difference in the results?
The time, I mean, we were not interested in analyzing the effect of the time length of the simulation because this is somehow fixed in the accident. So we are analyzing the accident for that time scale, and the approach, and we only use the approach that I described for what concerns the modeling and the processing of the data with respect to time.
He's referring to he's referring to a sequential training in time, in other words, in blocks of time instead of one shot in time.
No.
So there's a recent paper that several authors co-author about a unified version of that sequential in time. So you can see there it's in JCP. It's me and Kirby, Kirby, right? And Michael Penwadden is the first author.
Okay, but, thank you very much.
Yeah, so that will reduce actually the time for training because you have a smaller target to train. I have a question on the so you chose that one equation. I wonder if you try, because obviously you're doing partial physics, and I wonder if you try different to include different equations. If that would even with a 10 samples would give you a better result if you include some of the critical equations, but no more than one, for example.
This is something that we are currently working on. We didn't do for this work, but we are doing. We had some differences with respect to the results. So what we found is that adding the physics does what the physics does. So the equations that you saw and that we are analyzing is aligning somehow the temperature and the reactivity. So they are really well aligned in the simulation. If we use, for example, another equation that describes better, for example, the power related to the argmax, for that equation, we will have better results for the parameters and variables related to such equation.
So I don't mean to replace one, but to add, instead of one equation, have like 3, 4, 5 equations.
Yeah, we didn't do that yet. I mean, now we are starting with understanding what the different equations do, and then probably in the future we will also analyze the effect of adding multiple equations.
And the last line that you have is a very important topic. Zogren, one of the organizers here, is preparing a paper that will be on the archive soon. Zogren, do you want to talk about PIN model discrepancy and uncertainty? So Federico would know what you're doing. Zogren?
Yeah, we're working on that actually. The major problem is in a lot of the scenarios we misspecify physics, and basically the real physics and the assumed physics they're different. And how do we model the discrepancy caused by this model misspecification, and how do we model the uncertainty of that? So that's the stuff we're working on. And yeah, I think this could be related to your work as well.
It's
yes,
like
yes, I will be really interested in.
Yeah. Federico, the idea is that it's like a gray box. You assume a model, but then you add another neural network for in case the data don't fit exactly that. So then you discover the discrepancy.
Okay, so you model the discrepancy with another network.
Yes.
Exactly.
Yes.
Yeah.
I see, it's interesting. Because it's really interesting in this kind of applications because we are doing uncertainty quantification. So then our errors, we will have the propagation of our errors in the uncertainty quantification.
Yeah.
And this is something to be taken into account.
So Zogren wrote the paper Neural UQ, which is maybe you can put a couple of papers for Federico on the chat. The two papers. One is Neural UQ, the library. The other one is like same topic, but it's 104 pages. Paper on all UQ for neural networks, PINNs, DeepNet, and so on. But there the model uncertainty was not addressed. The discrepancy. In other words, what in PINNs? What if you specify the model, the wrong model? Can you recover? And the answer is yes, if you have data. There are some data.
Okay,
So,
I understand. This
we have a case of a non-Newtonian flow where we demonstrate that. Of course, we have PDEs, but then we have a case of non-Newtonian flow where we specify the model. Can you recover the missing part of the model from an extra neural network that you include? And the answer is yes, it is possible to do that.
I see. Really interesting.
Any other questions for Federico? No, maybe we can proceed.
So thank you, Federico, for tuning in today and for giving us this wonderful presentation.
Thank you, and sorry again for the technical issue.
No worries. Please feel free to stay for our second presentation. We have a presentation after this. So we'll move on to our second presentation. Our second presentation is by Professor Yanlai Chen. He would be talking about GPT-PINN, generative pre-trained physics-informed neural networks towards non-intrusive meta-learning of parametric PDEs. He received his PhD in mathematics from the School of Mathematics at the University of Minnesota in 2007. He worked as a postdoctoral researcher at Brown University before joining the Department of Mathematics at the University of Massachusetts, Dartmouth in August 2010, where he is currently serving as a full professor. His research interests are in numerical analysis and scientific computing, in particular, finite element methods, reduced basis methods, and other fast algorithms, uncertainty quantification, design analysis of machine learning algorithms, etc. With that, please join me in welcoming him for today's presentation.
Thank you very much. Let me try to share my screen. Do you see it?
Yes.
All right. I would like to thank George for the kind invitation and thank Sandata for the introduction and also Zongren for coordinating all the logistics. Appreciate it. So as you can tell right away, this is the GPT. This GPT is not the GPT that everyone is talking about yet, I guess. This is joint work with my student Sean Kui, that's funded by ISF and AFOSR. I explain the picture on the left bottom corner later. So what is this GPT? So this is a structure, what I'm calling a structure preserving acceleration of PINN. It uses the same, as we know, PINN has a very successful and celebrated structure. So the GPT-PINN speeds up the regular PINN in the parametric PDE setting, just like the so-called reduced basis method, which is an acceleration of finite element method under the parametric setting. And so this diagram is what I'm hoping to be a take-home message of the talk today. So here's the outline. I talk about the projection-based MOR briefly, and then I mention PINNs, and I talk about how the design of GPT-PINN and some of the details and its algorithms, and I'll end by showing you some numerical results.
We don't see the slide change. So
you don't see the slide change.
Maybe
That's a bit weird.
is a
Oh,
full
let me-
presentation mode. Yeah, we still
Let
see
me
the
just reshare. That because I went into full screen.
yes.
Do you now see the second slide?
Yes.
Okay, thank you for letting me know. Again, this is a diagram to show you what I was talking about, a take-home message for today. And the GPT-PINN is accelerator for PINN that preserves its tested and celebrated structure, just like RBM is an accelerator for finite element method. And I've been working on RBM for a few years. And this was the outline that I introduced. So there were quite a lot of multi-query contexts, such as some of the examples given here, optimization, inverse problem, and UQ sensitivity analysis. So while we have to run simulations repeatedly, and they're all in the same family of simulations, for example, scattering problem with different materials, different geometrical configurations. So the projection PMO is a method for this setting, and it's built on top of the traditional methods, be it find difference, find element, spectral, and I'm listing here a whole bunch of references, and the so-called linear reduction. Here is answers, the red line. What it does is that it tries to speed up the parametric simulation by building a problem-dependent basis. So here the these mu i's are selected in a greedy fashion by the method, and then you go on and use your favorite algorithm to simulate the u of mu I. And for any other mu, you use a linear combination of those bases to build a surrogate, just like finite element method, the solution is a linear combination of its bases, right? So you can sort of think of this as a spectral method with a tailored basis. So here I'm using the picture U1, U2, U3, and the traditional methods you have degrees of freedom, all those meshes, and for the PMO, you don't have those degrees of freedom anymore for each given basis. So I'm intentionally removing those grids. So this becomes one basis, and in the end, this problem, the degrees of freedom, is only the straight n. And of course, given any mu, the task is then to evaluate to find the C mu's, C1 mu, C2 mu, all the way to Cn mu. Just like finite element method, you need to find the coefficients. And that's, of course, an important step. So I'm calling here a parameter to code map. You give me a mu, how do I find those C mu's, all right? And I'm using a simple equation to show what the PMO is doing. Here is a strong form PDE, reaction diffusion PDE. I'm calling the blue term mu kappa C to be a parameter. And of course, here is the weak formulation. And what finite element does is discretize the spaces, discretize the forms. And we use the KLN here to denote this degree of freedom. And for linear problem, scalar linear problem, at the end of the day, you solve for KRM by KRM system. And the PMO, in particular RBM, reduced basis method, is basically one more step here. And it keeps the same formulation, it just changed to a different space. So here, instead of the red VH, we have the red WN, right? WN. WN is nothing but the three solutions that you saw from last slide that is spanned by those pre-computed solutions. So assuming the space is built up well for this problem, and its dimension is only straight n, which is much smaller than the calligraphic n, and again for the scalar, a linear problem, or non-linear, but then it's a system, it's a sequence of linear solve. So you are solving a linear system of size straight n by straight n now. presumably that can be done much faster, assuming the assembly is only dependent on n and not dependent on the KRM, right? So that's a one-slide introduction of PMO, in particular RBM, and there's a little bit of theory in the background. Why has RBM been so successful by many problems? It is the so-called fast decay of the Kolmogorov n weights. So here the dn is the distance between. Now we have this u cal d. So d is a parameter domain. So this u is a solution manifold. Here you're looking at the n-dimensional subspace, all right, and this is the distance between the manifold and the space. So the best such n-dimensional such n-dimensional subspace, the distance of that and the solution manifold is called the Kolmogorov n weights, and that's just a definition of that distance. So for many problems, in particular problem with some level of diffusion, these widths would decay very fast, exponentially fast indeed. So that means the solution manifold can be approximated well by a subspace, this Xn with you don't need n to be huge. So that's the theory behind. And of course, to identify this space as is an NP-hard problem. So computationally, the task is then how to construct that perhaps a suboptimal WN, right? And there I'm listing two approaches. The first one is a RBM type approach, as I introduced a little bit and already. So it uses a greedy algorithm where it exploits a posteriori error estimate, and it finds this WN one dimension at a time. I'll give a flow chart at a later time to give you more details. But the idea is you start from scratch. You build this space ground up by adding one dimension at a time. And in the end, you stop at this n. And by doing so, this n. By doing so, you only need n full order queries. You only call your expensive full order simulation n times. That's a method that I'm trying to emphasize here. Another type of method is POD type, essentially SVD. So what you do is that you do a priori sampling of the mu domain, right? All those different sampling approaches, but all those are a priori, right? You sample the domain, you collect all your solutions, then you do your SVD type of approach, you truncate it down to n. The keyword is down, right? So usually you truncate, depending on the criteria, you truncate a lot. So the consequence is that you ended up using a number of full order queries much larger than straight n. So I'm denoting here amount of form data is going from small to big when you move from RB, a greedy type approach with error estimation, to a POD type approach. And on the other hand, there has been some neural network approaches for this parameter to code map, this latent code map. And I'm just listing, very few of them. I'm sure that, a huge number of them are not here. So the first, the three of them, they're all great approaches. They design a particular structure, in particular the autoencoder and others. And the last one is analysis of this kind of approaches. What roughly speaking, what it concludes is that whenever RB works, you can find that exists a DNN that would approximate solution well, and to have similar accuracy. And the size of DNN is cubic with respect to the size of RB, the RB space dimension. So all these methods, the common feature is that once you train the neural network, when you give me a new mu, a parameter value, I need to produce a solution, and that solution is evaluated from the neural network. So you train it, and it's a simple evaluation when you have a new setup. In other words, it doesn't incorporate this new physics at this new parameter value. And so I'm using a data physics coordinate catalog for these approaches. This is clearly inspired by George's amount of data, amount of physics picture, a very nice picture in some of his talks, 3 toolboxes, I think. So this kind of like 2D version of that. So if you think about the amount of data, as I was trying to convince you, RBM use less data, POD use more data, and it both has physics, meaning you give me a new mu, I solve the corresponding PDE in some sense, right? And then the NN regression is down below, so it uses a lot of data, the labeled data, but you give me new mu, there's no physics built in, so less physics but more data. And speaking of neural network, there's as it's not breaking news here, everyone knows is a widely famous, successful neural network approach called PINN. I'm sure everyone knows it, but just for the completeness of the presentation, I'll devote a minute or two to that. So PINN, what PINN does is you parameterize the solution by a neural network, this NNWB, I'm calling WB theta. And that's, you give it a random start, that's your solution. And then you calculate your derivatives, you calculate your residual. The residual includes the mismatch with boundary and the initial conditions and the equation residual, or perhaps some data in the middle without the boundary or initial condition. Nevertheless, based on the MSE, you do your backpropagation, and you arrive, with some convergence criteria, you arrive at your theta star. All right, theta star. Then I'm replacing my traditional solution, UXT, by this PINN solution, the PC and theta star. Okay. So above there, just structure of the PINN. So, of course, as somebody who worked on parametric PDE setting, model reduction setting, first question is, can it handle the parametric PDEs? All right, and the answer is yes, but I would say that some challenges. So of course, PINN as is can solve inverse problems. So it has been handling parametric settings using, say, you put parameter as another input. And I would say the network is then gets larger and you need more training and perhaps more tuning of the hyperparameters. And given the specific mu, again, it does not have as much physics as the original PINN. And if you just look at this theta star, this convergent neural network configuration, this theta, right, WBs, it usually is high dimension because we tend to over-parameterize the solutions. And so the training takes time. And now if that is in the multi-query setting, you need to train it every new mu. This is really not affordable. And a deeper challenge here is that if you look at this data, if you take a look at this, you sample on the new domain, you just train a whole bunch of pins, and you look at this data, and it's clear for many problems, this data does not have a low rank structure, even though the solution does have a low rank structure. All right, so the typical thing that we play with to leverage the low rank structure wouldn't work here. And there have been quite some attempts, I would say, in this domain lately. And the first one, I'm here listing a paper, the type of program calling PINN plus X. So the idea is that, well, I'm going to find out this theta dependence on mu. I probably do some labeled data, and then for the others, I do regression. All right, or perhaps using some standard meta learning approaches. LEAP. So that paper showed the regression interpolation type of approaches are better than ML and LEAP. But still, not as good as if we were to fully explore the physics, which I'm showing today. The second row is DeepNet FMO. I would say they are, again, with oversimplification of all these great results. So this is more of a POD-based thinking. You are sampling the input function space pretty pervasively, and there's a meta node, and over there you're transferring the theta. You account for the parameter dependency in one layer and transfer the other layers. So up to now, all this again is all data driven, and when you have a new mu, it's again an evaluation of a trained map. And there was another approach called PRNN. Well, here in the training of the map, there's some residual built in addition to the labor data. So it ended up using a bit less data. But again, the common feature is the same. When you give me a new setup, just evaluate the trained map. So this is the cataloging again. I'm putting PRNN on the lower left, DeepNet FO and others on the in the parametric setting. Again, I'm talking about on the lower right. So there's as far as I knew nothing in the second quadrant that you use little data, but you build in physics for just like PINN for every mu. And I'm arguing that's where exactly the GPT-PINN is located. And so how is that possible, right? So we go back to the RBM answers, this mathematically sound answers, and that's what inspired the GPT-PINN design. So here again, this is the linear combination. We have Ci mu u mu I, right? And what PINN does is that it replaces u mu I by our PINN solution. Okay. And if you take a look at this, it's again the linear reduction. It's nothing but one hidden layer, zero bias, a much small network, given assuming the straight n is small again, which was shown to be the case by RB. And I'm calling this 2n1 network. And this straight n is nothing but the width of the hidden layer. All right. And my C's are just weights at the ith node. And the most interesting is the final one, the final one, the persistent I. Those can be sort of as a customized activation function, right? So it's not a, if you think of this as a layer, so this was is a traditional activation function like ReLU, sigmoid, and tan-H, and whatever you are using. And so this formulation tells us, well, you cannot use any of those. You have to use a customized activation function, a full PINN basically there. And so here you go. This is a schematics of the GPT-PINN. So it's a one hidden layer network, and in the middle, every neuron has nothing but a full PINN. The pre-trained. And again, I have a flowchart later to describe to you how we build this from ground up. But there are full PINNs and pre-trained as some representative parameter values. And then once I have those, some number of them in the beginning is 1, 2, 3, and so on and so forth. So let's say I have I of them, right? So then I have this way C1, C2 to Ci, and I form a surrogate solution U sub I would be. And exactly the same structure as PINN, and then I evaluate my derivatives. You give me a prompt, a mu. I'm computing the MSE, right? I have my corresponding governing equations and boundary conditions. I can evaluate a MSE, a loss, which just like PINN includes, what is usually included. And then the backpropagation would help us to train for the C1, C2 to Ci's and weights. And I'm denoting this loss by L GPT-PINN C mu, right? Just for later formulations. And one last message here is that this hidden layer is growing one by one. So I'm adding these neurons one by one. To the extent you are happy with accuracy of this surrogate solution UN. And some of the, again, there's more to talk about for how we build this up. Just hold on a little bit. I go on talk about some features. So first of all, it embeds physics because you do a gradient descent on your C, and the loss includes residual BC and the IC. So there's physics in it, just like PINN. And it needs small form data, just like RBM, not POD. The number 4 PINN queries is just n. You ended up using 10 neurons. You only query the 4 PINN 10 times. There's no truncation from more data, and it has meta neurons in the sense that the neurons are customized for the problem at hand, and it's non-intrusive, which is a feature that we found very important and convenient. You can plug in any existing PINN to your hidden layer, plug into to the neuron. And the meta network training of the, you find the C, that part, you don't need to know the details of the underlying PINN. You just need to be able to evaluate the PINN solution at your collocation points. In fact, I'll show you an example of Alan Khan, for example. We just took a nice adaptive PINN somebody else developed, just plugged it in to our GPT-PINN, and it works very nicely. And it accelerates PINN. It's 2 to 3 orders of magnitude speed up. This is that I give you more data when we talk about numerical results. So it is a PINN accelerator. And a little bit of insight. I think all these things work because of the derivatives is essentially linear operation, and the PINN is essentially collocation in nature. So and the other standard trick, just like RBM, is that you pre-compute. It's a very important step. Whenever you find a new dimension of your surrogate space, you pre-compute your values and derivative at those points. You keep expanding like that. It's after those, the speed up is possible. And a missing piece so far, in addition to a flow diagram, flow chart that I've been promising you, is this a posteriori error estimate. So the traditional RB use error estimate to guide the selection of the dimensions of each dimension of the surrogate space, and it also satisfies the accuracy of the eventual surrogate solution, and just like many traditional finite element type of analysis is based on the residuals. It's in fact just derived from a standard finite element analysis. Well, what do we do here, right? For PINN GPT-PINN, well, this is not rigorous, but the training loss of this small network with NNR to N1, that just like again the traditional PINN, you have residual. That loss is residual. So we propose to just take that loss as a error indicator. So that would guide me to build this algorithm, which I'm describing on this slide. In the beginning, you know nothing about the parametric dependence of your solution. You set it up. You have your training set. Here is C train. Is presumed to be discretized. Then I have you have a full PINN developed for a given mu. And again, you know nothing so far. You just take your first one randomly, or maybe you take the center of your domain, right? And that's what we've been doing for the numerical tests. And your n is 1, you set up basically an empty GPT-PIN. And now you know your mu1, you go ahead and call your full pin at that mu1. And you update the GPT-PIN, now n is 1, right, by adding the fourth neuron. So you have a 2-1-1 network for time-dependent problem. That's your little GPT-PIN. And then you go ahead and solve, basically you're only solving C1 now. You train one scalar, right? You solve your 2N1 network everywhere on your parametric domain. Okay, it's a discretized parametric domain. It's very quick because it's a very, very small problem. Again, for traditional methods, it's just 1-by-1 system in piece of cake. And as you go around the parametric domain and solve each reduced problem, you record your C and your terminal loss, by whatever number of epochs or whatever criteria. You record this error indicator everywhere on your parameter domain. Now you take a look at the parameter domain and you see, well, you ask, is the maximum lower than tolerance? Or in the beginning you only get one neuron, of course, is no. So what you do, you take the highest location, right, where the error indicator, error estimator is the largest, right? And you take that to be your second location. That's a standard greedy type approach. So basically, you whack more gain. You whack the highest. If you use a current surrogate solver, you're going to do the loudest job at these locations. You better include it, right? Then if you do that, at least traditionally, if it's a coercive problem, the next time the error will be 0 because it's already in your space. And you do your optimization problem, you recover the exact solution at that location. So all of a sudden, your highest error becomes 0, right? So that's an intuition of this type of greedy idea. And of course, we're not having the exact error, we're having error estimator. So this is so-called the weak form, right? So you take your mu2 basically now, and you go back up, all right? Now you have your mu2, your n is equal to 2. You solve for your pin at your mu2, and you keep doing this loop. You repeat a few times until this maximum error indicator or estimator is below the tolerance, and that's when you stop. So this is this is what I meant by this hidden layer is growing one at a time. You find one neuron at a time, and like this. And let me show you some numerical results. We tested on Klein-Gordon and Burgers, viscous Burgers, and Alan Kahn with 1, 2, 3, up to 3 parameters here, baby problems. So here is a setup for the PIN and the GPT-PIN, just the hyperparameters, architecture, activation functions, and those things. And I want to call attention to that the GPT-PIN, the learning rate of GPT-PIN can be set larger than the learning rate of the underlying PIN, and the epochs is much lower than the epoch of the underlying PIN. And a little bit detail when we work with the Burgers problem, because we set the here is a 0.005 to 1 the viscosity. So when the viscosity is smallest, you have near discontinuity. In that case, you don't want to include the collocation points close to the discontinuity. So what we do is just a simple ad hoc approach. We just trimmed those points away when the second derivative is larger than the top 20%, the locations of top 20% of the second derivatives. We trim those away. We just collocate with the reduced network on the other points. And here's it's good location to emphasize that the small network, the collocation sets of the small network is very much independent from that for the full underlying PIN. So here is the training result for Klein-Gordon, And this picture shows the location of the parameter value selected by the algorithm. So here is largest loss, the worst case scenario when you increase number of neurons, and the black curve is what we're calling the adaptive neuron, is what was described today. And just to show you this idea of using a full pin as a neuron, right? How powerful this idea is by including this red curve. Red curve is nothing but everything is the same, but you don't do this greedy. You just uniformly choose a few. Like maybe you take the first 3D cube, you take the corners and the middle of each square size, like that, right? A priori, you just do a uniform sampling and just train your full pin there and use that pin as an activation function. It's doing pretty well. It's worse than adaptive way, but doing pretty well. This picture is just more statistics, and below is a 3 full pin solutions selected by the GPT-PINN. And we tested. Here is a test. The largest error for a test set that's outside of the training set. And here's more statistics in the middle. I want to call attention to the right picture, the picture on the right. So here is a time, the cumulative time, as we increase the number of test cases. So you keep calling your PINN or your GPT-PINN after its training, up to 200 evaluations. So of course, the black one, you have a non-zero start time. That's our training time, right? That you build up your GPT-PINN, or all the time from the very beginning was included in that. And afterwards, because it's a such smaller network, every time you run an additional query, it takes very little time. It reflected from the slope of the black curve is much smaller. It's basically flat in comparison to the red line. The red line is proportional to to one solve. The slope ratio is basically the speed up. The marginal speed up is 454 here. And if we include the off-line training time, right, you look at the intersection point. Where do these two curves intersect? And that's where, in what situation is it worthwhile for you to invest in the GPT-PINN training, right, to build it up? For Klein-Gordon, I mean, by the way, because you have 15 neurons, so at the very least, you need 15 times, right? This intersection would be at least 15 because you call your PIN those many times. And what we're showing here is, given a reasonable implementation, this is probably 25, 26. So it's not much more than, the number of neurons you need to build. So the overhead is quite low. And here is some more pictures of the PIN loss as a function of epoch, and the same picture for GPT-PINN. It's for these problems, it notably smoother decay than the underlying PIN. So this is a Borger's training. Here is clearer. If you look at the picture on top, is clearer. The location of the chosen parameter values. So again, it's not a priori. It's not any a priori sampling. It's determined by the algorithm. So we start from the middle, and then the algorithm knows right away to go to the two ends, the two extreme values, and then you keep basically asking for more values toward the lower, smaller viscosities, and once in a while you go to the other end. So this shows the location, shows the dynamics of this greedy algorithm, and we only took 9 neurons. So the network is only 9291. This tiny network. It works pretty well. It's three digits in loss. And here are the picture below are the 3 full PIN solutions. So those activation function used by the GPT-PINN. That same picture. So now we do the testing, and again, the relative error in 2 digits. And if you look at the cumulative runtime on the right, we need, with this implementation, again, at least we need 9, but here we need like 12, somewhere between 12, a little bit more than 12. So the overhead is quite little, and the marginal speed up is more than 100. And the loss picture. And I want to talk about the Alan time. So Alan time is as well known in the community. You know, the vanilla pin wouldn't work well for Alan time. So people have been developing, you know, a more refined approaches to make it work well. In particular, there is a SA pin by McClany and Brago Neto in 2020. So we took that one, the code that is kindly shared, and we took that one and used that as our underlying pin. And this would be, you know, the lambda epsilon, the parameter distribution chosen by the GPT-PINN, and again the largest loss and most statistical loss. And these three are the first 3 activation functions in the GPT-PINN. And testing is similar type of performance. And here the slope ratio is a lot higher. The reason is you know, because it's adaptive pin is more expensive than the vanilla pin, which shows the power of the GPT-PINN, because GPT-PINN is equally expensive as, you know, other as a GPT-PINN based on vanilla pins. So the speed up is more dramatic than the last 2 examples. So it was 9, at least 9. We ended up, you know, less than 10, a little bit more than 9. Again, shows the overhead is quite low. Here is a loss as a function of epoch. For this one, the underlying pin use Adam and followed by BFTS. So let me conclude. So we designed the first, what we think is a first pins accelerator. It is RBM framework for the, you know, the very successful pins. It preserves the pin structure, and you know, the physical conforming property of it, and it relies on minimum amount of form data. So there's no POD type of things or truncations. And it's non-intrusive, it's more portable. And it adopts for pin as single neuron and relies on, you know, a loss for guiding the greedy construction. And it naturally features offline online decomposition, that those pre-compute strategies that I was talking about can be done for nonlinear, non-affine problems. So in principle, because this is built with RBM philosophy, in principle, any problem that RBM works, if you have a pin for that problem and you want to do parametric study, GPT-PINN would work, because, you know, it's based on the same rationale. And it's to the QR code for the paper, and the code is also available online, and here's my email address. And again, I acknowledge support from NSF and AFOSR. And I also want to give a shout out to 2 entities on UMass Dartmouth. One is a math program by Dr. Bala, and another one is our Center for Scientific Computing and Data Science Research. All right, that's it for my talk. Thank you very much for your attention.
Thank you, Professor Chen. We can have a couple of questions for him. Yes, Eric.
Yeah, thanks for the nice talk. This is a area that's very important to me, this kind of problem space of small training data. So I'm trying to connect a little bit with your GPT-PINN architecture, in particular the generative piece. What it seems to me is that you're sampling in this offline model, you're sampling all these points. I don't quite understand given the prompt mu, and then how all these operators, that previous slide, all these operators, how these relate. I guess I'm a little bit lost in that.
So that's thank you for the question. That's basically the parametric problem that's given to us. In principle, if you have an explicitly given parametric equation, maybe its frequency of your problem, maybe it's computational domain, shape of the domain, or even a boundary condition, initial condition, then every time you have a new parameter, you would have the corresponding equation. All right, the equations are the same type of equation, but it's different because the value of mu is different. With that said, you could have situations where the parametric dependence is not as clear. But as long as you can have something is changing, and then you have the corresponding physics, as long as you are able to evaluate the loss of that corresponding physics. Does that answer your question, Eric?
I think so, yeah. Thank you.
Sure, thank you.
Do we have more questions for him? Okay. If not, thank you, Professor Chen, for giving us this presentation. And with that, we come to an end for today's seminar. The recording of today's seminar would be uploaded on our YouTube at Crunch Group. Please feel free to follow us over there and have a great rest of the day and a great weekend ahead. Thank you.
Bye, everyone.